Here's a kind of problem about integrals that I often put on exams, and you had some homework problems like this. You're given a graph. Probably it's simplest to keep it to be a piecewise linear graph made up of pieces that are straight lines that is supposed to be the graph of the derivative of some function. And from that graph, and maybe a little bit more information, we try to draw the graph of the original function. I like to pick an example like this. Maybe it's the graph is horizontal for a little while, and then it goes down along a straight line like that. And we can pick some values here. We can say maybe it's equal to 2 when x is between, say, 0 and 5. Then it crosses the x-axis when x is 7. And let's say it's goes out to x equals 10 here. And if that is x equals 10, and if this line is a straight line with a constant slope right here, it looks like this is going to have to be -3 right there. So this is the graph of some function. You could call it little f of x, but I'm going to think of little f of x as being the derivative of some other function, capital F of x. So I'm graphing a derivative. And I'd like to graph the original function capital F, which is going to be an antiderivative of little f. That's the goal. We're also going to assume something else about f. It's often the case that you assume capital F of 0 is something, but I'm going to throw a little wrinkle in it. And I'm going to assume capital F of 3 is 1. And my goal is find values of capital F and graph it. And let's add on a goal. I'll call this goals. And find a formula for capital F. I don't always ask to find a formula, but I'm adding that on here. Let's also find a formula for capital F. Now, the formula for little f, you can see here, because little f is made up of two pieces that are straight lines, not the same straight line, would be a piecewise formula. Let's go ahead and write it down. I don't always do this on these kinds of problems, but it can be done. Little f of x equals 2 if x is between 0 and 5. And what does it equal if x is between 5 and 10? Looks like a line with a slope of -1, right? Rise over run, if you focus on, say, these 2 points here and here. The rise is -2, you go down 2, and the run is +2. Rise over run's -2 over 2 is -1, is the slope. Actually, here's a quick trick you can write on the formula. You also see it's got an x-intercept at 7. You could write this as negative, in parentheses, x minus 7. If x is between 5 and 10. That's an x minus 7 if you can't quite tell. Of course, you could distribute the minus sign through the parentheses there. You could also write that as -x plus 7. Emphasizing, yes, the coefficient of x is -1, the slope is -1, and the y-intercept is 7, and I could write that down because of this without trying to figure it out by looking at the graph. But if you did go backwards here, the slope is -1, so as x decreases by 5 from 5 down to 0, y would have to increase by 5 from 2 up to 7. This is not part of the graph, but that would be a 7 up there. But it's not part of the graph of little f. So how do we do this? How do we find values of capital F and graph it? We need to use the fundamental theorem of calculus. Now again, mostly we've used the fundamental theorem of calculus to evaluate definite integrals. Here's a definite integral. How do you figure out what it equals? Find an antiderivative. Capital F, do capital F of B minus capital F of A. This kind of reverses it. Here we have a graph. We can easily find values of the integral by thinking about areas because we've got straight lines. If these were curves, it would be harder. You'd have to be given the areas like you had in some homework problems if it were a curve. But here we can figure out the areas pretty easily. We're going to use those areas, or more precisely, those signed areas when the graph goes below the axis, to find values of capital F. Okay, we can make a table of values like this. X and capital F of X. Let's go ahead and find values of capital F at 0, 1, 2, 3, etc., at whole number values. Some of these we'll be able to figure out pretty quickly. So I'm making a big table here. The one that's quickest to find out is the one that you're given, right? F of 3 equals 1. I'm assuming that. Why? Because I feel like it. That's why. No application in mind. I'm just saying pretend F of 3 equals 1. I could have picked some other number. F of 3 is 1. That's the given information. How do I find the other values? What's F of 4, for example? Capital F of 4. Use the FTC. Use the FTC and think of it in this way. The change in capital F over any interval that I want from A to B, well, by definition, that's capital F of B minus capital F of A. You find the total change in the function over the interval from A to B by integrating its rate of change. Its derivative. And that derivative is what I'm calling little f. It is the graph that's above. And the goal here is to think of this in terms of areas, not in terms of the formula for little f. I'm going to ignore the formula. I'm just going to focus on the graph. This is better for this problem. So the change in the value of capital F, as for example, x increases from 3 to 4. So if A equals 3 and B equals 4, what's the change in F? It's the integral from 3 to 4 of its rate of change of little f. Little f is its derivative. Capital F is an antiderivative of little f. And what does that integral equal? It equals the area under the curve from 3 to 4. Area of a rectangle. Rectangle has base 1, height 2. The integral is equal to 2. That's the change in capital F. As x increases from A equals 3 to B equals 4, as x increases by 1 unit. Therefore, the value of capital F at 4 is not 2, but 1 plus 2, 3. The 1 comes from the previous one. The 2 comes from the value of the integral. Add them, get 3. 2 is the change in f, capital F. 1 is the starting value of capital F, so to speak. So the new value of capital F at this new value of x is 1 plus 2 is 3. That is the next value of capital F. What about when x is 5? I won't write it down. Well, maybe I should write this one down. If A equals 4 and B equals 5, so x is increasing from 4 to 5, delta f. Delta of capital F is the integral of little f, its derivative from 4 to 5. But the graph of little f is still constant at 2 when x is between 4 and 5. So that integral, that area, is still 2. This is a 2. So the new answer is 3 plus 2 is 5. The 3 comes from this 3. The 2 comes from this 2. The new value of capital F is 5. As x goes up to 6, it is a little trickier. If A equals 5 and B equals 6, what's the change in capital F? It's the integral of little f, its derivative from 5 to 6. However, that's a trickier area to calculate. It's no longer a rectangle. It's not even a triangle. It's a trapezoid. right there in green. Base of 1. The height on the left is 2. The height on the right is 1. That's 6. This is 1. Slope of that line is -1. Area is base 1 times the average of the two heights, 2 plus 1 over 2. 3 over 2, 1.5 is the change in capital F, because that's the value of the integral of its rate of change. So coming back here to this table, the new value of capital F is the previous value 5 plus 1.5. 6.5 is the answer. I guess I am doing most of these by thinking about the picture here. Maybe all of them. You got to be careful here. What about as x goes from 6 to 7? I won't rewrite the integrals every time now. As x goes from 6 to 7, the change in f is the value of the integral from 6 to 7, which is the area of that little triangle right there. 1/2 base times height. Base is 1, height is 1. Area is 1/2. Area equals 0.5. So the change in capital F is 0.5. It goes from 6.5 up by 0.5 to 7. As x increases from 7 to 8, the change in capital F is given by the integral of its rate of change. But now that's a negative value, because the graph goes below the x-axis, the graph of the derivative, little f. The area of that triangle by symmetry is positive 0.5, but the integral is negative 0.5 because the graph's below the axis. So when you take the previous value, 7, and add on the value of the integral, negative 0.5, that's like doing a subtraction. It brings you back down to 6.5. 6.5 is what I'm trying to write there. That's a decimal that you can hardly see. As x increases from 8 to 9, what's the value of the integral? It's the opposite of the area of this trapezoid. By symmetry, it should be the same as the area of that trapezoid. 3.5 or 1.5, excuse me. But the integral, therefore, is negative 1.5. So f goes down in value. Add negative 1.5 is the same as subtracting 1.5, goes back down to 5. We've got some symmetry going on here in the values of capital F. Once I go from 9 to 10, though, it's not quite the symmetry matching, because the graph is continuing downward here. I want the area of that trapezoid. Base is still 1. Two heights are 2 and 3. The average of 2 and 3 is 2.5. Base 1 times that average, 2.5, gives you an area of 2.5. So the value of the integral is negative 2.5. So we go from 5 down by 2.5 to 2.5. How about if x goes backwards? It's like time running backwards, like you're watching the video in reverse. What if A is 3 and B is 2? What's the change in capital F? A little strange. We put the bigger number on the bottom and the smaller number on the top. By convention, because it makes sense, that's the opposite of the integral I get where I switch those around in the ordinary way. That's a definition. Why do we define that in this way? Because it makes sense in applications. That's why. The integral itself is the area onto the graph between 2 and 3, which is yet again another rectangle of area 2. The integral has a value of 2, but I have this negative sign in front of it, so the answer for the change in f is -2. As x decreases from 3 to 2, capital F goes down by 2. So up here, I could write 1 plus -2 is -1. This is going to make sense graphically too. Capital F is going to have a graph as x increases that is linear here with a slope of 2. It's going up by 2 every time that x increases by 1 until you get to this point. Ignore everything down here. A straight line with a slope of 2. That's got to be the case because this is constant with a value of 2, and this is the derivative of capital F. The slope of capital F is constant at 2 when x is between 0 and 5. X goes from 2 down to 1. Once again, we'll have an area of 2. F will go down by 2. -1 plus -2 is -3. And the same kind of thing happens as x goes from 1 down to 0. All right. So now the graph of capital F. What will it look like? I could plot points. F of 0 is -5. F of 5 is 5. It's going to be a straight line with a slope of 2 when x is between 0 and 5. Notice that f of 3, this is not obvious, but it's true, is 1. There's our given initial condition, so to speak. Capital F of 3 was 1. Then you could plot these other points. When x is 6, y is 6.5. When x is 7, y is 7. Something about like this. The rest of the graph looks about like this. Looks kind of like a parabola. Is it a parabola? Yes, it is. Why? Well, the derivative of a quadratic, whose graph is a parabola, is going to be a linear function. Hey, this part of the formula is linear. It's got to have a derivative equal to -x plus 7. It's got to be an antiderivative of -x plus 7, which is going to be a quadratic. So there's about what the graph of capital F of x looks like. Straight here, parabolic after that point, concave down. What about a formula for capital F? It's going to be piecewise. Straight line with a slope of 2 and a y-intercept of -5 if x is between 0 and 5. Remember, I said just a minute ago, when x is between 5 and 10, it's got to be an antiderivative of -x plus 7. Indefinite integral of -x plus 7 is -1/2 x squared plus 7x plus c. When you do the indefinite integral, the c is arbitrary, but our particular capital F is not an arbitrary function. It's one particular function. I need to figure out what c is. I do know that when x is 5, for example, the formulas have to match up at this point. This graph has to be continuous because it's got to be differentiable. The derivative of capital F equals little f. If f is differentiable, it'll also be continuous. So I do know that with the other formula that is related to this, that when I replace x with 5, I got to get 5. That point right there is 5, 5. So if I replace x with 5, in this expression, I'll get negative 25ths, 5 halves. 5 squared is 25. 7 times 5 is 35, which I'll write as 70 over 2. So I get a common denominator of 2. Plus c, and I want to set that equal to 5. That's the y coordinate. It just happens to be the case in this example that the x coordinate equals the y coordinate there. That wasn't a guarantee. I didn't know that was going to happen ahead of time. So for c, c is going to be 5 minus negative 25 plus 70 is 45. So we get 5 minus 45 over 2. 45 over 2 is 22.5. So it looks like we get negative 17.5 if I have not made a mistake. So the formula for capital F over here, negative 1/2 x squared plus 7x minus 17.5. No. Yeah, that's right. Okay. I'll just write it as a decimal. That would also be the same as negative 35 over 2. That's if x is between 0 and 5. 5 and 10, excuse me. If I've done it right, these functions should match up and be continuous when x is 5. They have the same limiting value when x approaches 5. Yeah, 2 times 5 is 10, minus 5 is 5. Let me just double check this one. Negative 0.5 times 5 squared plus 7 times 5 minus 17.5 should be 5. Yeah. So there's the piecewise formula for capital F. Okay, so I did a little bit more than you had to do for your assignment. It's something you should be able to do. More commonly, I just ask for a graph. Do you really on the test have to make such a humongous table? I usually make a smaller one. It's usually a problem with fewer values of x to figure out the values of a capital F for. But the principle still holds. You should be able to think about it in this way and think about signed areas. In a sense, when doing this, we are constructing an antiderivative of little f. If that's the given little f, this process of thinking about these signed areas and making this table, and ultimately this formula, is constructing, mathematically constructing, building an antiderivative of little f. Just one of infinitely many possibilities. You can also shift this graph upward or downward and get other derivatives of little f. That principle holds more broadly, and it's useful more broadly.